Alright guys, we're starting the last lesson before we have our Chapter 3 test. This is all about having a region defined by a bunch of constraints, which are kind of, if you think about it, it's like when we were doing inequalities yesterday, I gave you a bunch of inequalities, a system of inequalities, and we found the solution that we wanted to look at. That's what this is. This is a system with 4 different lines where they intersect are these points. And then we want to minimize or maximize this value. Okay? Usually I'll give you a C value that I want to minimize or maximize using this function down here. Or using this graph down here, I should say. So where the mins and maxes happen are at each point. You have to figure out which one is a min and which one is a max by using these points into that equation. So let's look at this one first. I have for this point here, C is equal to 3 times 2 plus 5 times 3. So the cost, or the C value here, is 21. Down here, C is equal to 3 times 6 plus 5 times 0, which is 18. Over here, 3 times negative 1 plus 5 times 2. And it's negative 3 plus 10, so we get 7. And down here, we have 3 times negative 2 plus 5 times negative 1. So you get negative 6, negative 5, which is equal to negative 11. So you look at the 4 numbers we got, and hopefully you guys see that this is the max point. So whatever problem I'm doing, the maximum value that we'll get using this function will be at 2, 3. The min point will be at negative 2, negative 1. So this is our min. Okay? So we used the graph into our C function, and we saw which one was min, which one was max. So that one's pretty easy because it's bounded by 4 points. This one's a little more challenging because we have nothing, it keeps going. It's not bounded all the way. So like this keeps going, it's shaded forever. Alright. All I have are 2 points. So let's test these points first. So I have C is equal to 0 plus 5 times 2, which is 10. And I have C is equal to 1 plus 5 times negative 1, which is negative 4. Okay, now we don't know what is max and min yet because we don't know what this function does. Okay, so let's pretend this goes on forever. If this goes on forever, I'm going to have the point, let's just pretend down the line, we're going to have the point 20, 0 in here. That'll go on forever. If I test that point, I get a C value of 20, which is bigger than both of my points that I tested. And if I keep going to the right, because it's unbound, and this is called unbounded, by the way, because it's not bounded by another line. If it keeps going, that means that this will always get bigger. So there is no max. So you would say there is no maximum here. But because there's no maximum, we do have a minimum. Our minimum will be negative 4. Okay, at the point 1, negative 1, because that will be the minimum value. But there is no max because it goes on forever to the right. And whenever you pick points that fit in here, into this C equation, it'll always be bigger. So that is testing constraints. Now we're going to do the same thing using, again, our objective function, C equals 2x minus 3y. The reason why this is the objective function, I wasn't using that up there, but it's the object of what we're trying to get. So in our word problems, it's usually the function that we're trying to minimize or maximize. There's a reason for it. And then we have these constraints. So this kind of combines yesterday and today. So let's graph our lines first. We have x is greater than negative 2, so we have a solid line. And remember, in this, I know up there, they shaded the regions that we wanted. However, we are going to do these problems by shading false. shading false. So we have x is greater than or equal to -2. Well, that will be to the right, so that means I want to actually shade to the left for that one. So we're at the left. And you guys could probably set this problem up on your own. So there's that. I have the equation y is greater than, I should probably do that as a different color, y is greater than or equal to -1. So here's this line right here, and again it's not dashed because it's equal to. I want greater than because 0 will work. 0 is greater than -1. So I actually want to shade below that. So I'm shading down here. Okay, and then finally we have this line, x plus y is greater than or equal to 4. So again, you can do the cover-up method. If x is 0, y is 4. So I have this point here, and if y is 0, x is 4, and it has a slope of 1. So if you want, which actually will make life easier because you can clearly see where these lines intersect, we can put those points in, and then it's a solid line again. Okay, now it says I want less than that line, so 0, 0 works. Again, we want to shade false, so we want to shade above that line. So there's my last shading. I'm shading false, and we have a nice little area for our constraints. So this is like the shaded area up there, but it doesn't matter. So we need to get our points from this graph to test where the min and max are. So I have these 3 points. I have the point -2, 6, and then hopefully you guys can see that these are clearly the points. -2, 6. I have the point -2, -1, and I have the point 5, -1. Okay, so now we have those points, and we want to use our objective function to solve that. So I'm going to do this point first. C is equal to 2 times -2 minus 3 times 6. So you get a -22. The second point, we get C is equal to 2 times -2 minus 3 times -1. Well, that's -4 plus 3, which is a -1. And the third point, we get 2 times 5 minus 3 times -1. So you get 10 plus 3, which is 13. Okay? So find the maximum minimum values of the objective function. So the maximum value is 13. That's the max. And it takes place at this point. And the minimum value is -22, and it takes place at that point. And if you want, and the reason why we pick at these points is the mins and maxes will always happen at these points of intersection. If you pick like 0, 0, that's in the, this will work for all 3 things, but when you do 0, 0, you get a C of 0. That's not a min or a max. It's in between -22 and 13. So we always test those points. Alright, so we're going to use that reasoning to actually do this next problem. And now this is the one where it's a big problem, so you guys will want to take a piece of that graph paper probably off the back of your packet right now. And you're going to need to have that separate just so you can work on this. So, the music shop problem. The key to this is we need to come up with all these inequalities. See how I gave you these 3 right here? Well, in our problem, we have to come up with that. Okay? So, Jake Garcia opens a music shop in which he sells guitars and basses. Well, I'm going to call these G's and B's, okay? And I chose to make X B just because I did that. I don't know why. Probably because of just graphing. B is easy to remember as X, and then Y is G. Doesn't matter though, unless I say. Let's actually say it. Might say later. So we have B comma G, basses and guitars. We're talking about actual physical instruments. So each bass will cost him $900, and each guitar will cost him $750. He buys B basses and G guitars. Write an equation for the total number of dollars C he will have to spend. So this is our objective function. We always start with this. It'll be $900 times each bass and $750 times each guitar. Okay? That's all we're doing with that function right now. This is the thing we're going to be testing later to see what the max and minimum cost will be. Because that's what we're trying to do. We're trying to minimize or maximize, well, probably in this case you want to minimize the cost for guitars and basses. Why would you want to spend more money? Okay? But here's the thing. Jake has certain restrictions on the number of each kind of instrument he can stock. So write a system of inequalities expressing these restrictions. I do not need the system to be all one big thing. You can write each equation out separately. Okay? So let's do this. We have his store is small, so he can buy no more than 50 instruments total. So our first equation should be that, and this is kind of like the mixture problem, our total amount, B plus G, except for it's an inequality, can be no more than, so it can be less than or equal to 50 items. Okay? Now, I'm going to turn this into slope-intercept form, just because when we're actually going to have to graph these lines. And remember, I made my G my Y, so I'm going to say G is less than or equal to negative B plus 50 instead. So this is one of my equations. I'm going to box the equations we're going to graph. Because guitars are more popular than basses, the number of guitars must be at least. So the number of guitars must be at least, so greater than or equal to the number of, twice the number of basses. Okay? And finally, so that's a y equals equation. We're good there. I'll graph this later. To get started, he must buy at least 17 guitars and at least 5 basses. So that means that basses must be bigger than or equal to 5, and guitars must be bigger than or equal to 17. You can't have less to stock the store. So it says plot the graph of the system in part B. We're going to be plotting these 4 equations. Okay, so get your graph paper out now. Pause if you need to. I'm going to go to the next page and I'm going to start plotting this. So what I did was I made each marking 2. So I just have to get the graph paper up. Okay, once you have your graph paper out, we now want to graph this. So this is going to be B, which is the number of basses. And this is going to be G, which are the number of guitars. And then I made these go every 2. So I said this was 2, 4, and so on and so forth. 6, 8, 10, 12, 14, 16, 18, 20. And I kept going just to have them. One, 2, 3, 4, 50. I went up to 50 because we know that 50 is the maximum amount of instruments we can have. So I did the same thing in this direction. We got 10, 20, 30, and 50. Okay, so there is my grid. Now, let's look again. We're going to have to flip back and forth a little bit here to see our equations. So let's look at this one here again. We have G is less than or equal to negative B plus 50. Or you can think of it as this system here. Again, you can do the cover-up method. When B is 0, G is 50. When G is 0, B is 50. And there's a slope of negative 1. So when there's the slope of negative 1, when there's a slope of negative 1, like I was saying, you can just graph it. So we know our intersection points are up here at 50 and down here at 50. And to make it cleaner, it might be easier to just put all the dots in. Or you can have a straight edge and go that way. I'm just going to do this so it looks okay. And hopefully we hit the 50 like we should. And since this was a greater than or equal to, less than or equal to, then we want to make sure that this is a solid line. Okay. So it said we want less than or equal to. So that means that if we want less than or equal to, we want a shade false. That means I don't want this stuff here. I don't want anything. Because think about it. We can't have more than 50 instruments. So I do not want this. I shade the thing I do not want. Because I want to look at what I want. So I'm going to shade this in one color. So we got the red line is the first equation, and we have that. All right, let's look at the next equation. Okay, so like I said, the red line was this one, so I'm going to box this in red because I used red for it. The next inequality, I'll use blue. G has to be greater than 2b. That means I have a line that starts at 0, 0. My starting point is 0, 0, and it has a slope of 2 over 1, right? Think of this as y equals 2x. Okay, so I'm going to graph that on my graph. This will be a solid line, so we want to make sure that it's a solid line when we do this. There's a point, there's a point, there's a point. I'm going up 2 and over 1. And that's pretty much all I need to do. Alright, so you graph it. Again, it's a solid line. And there we go. Okay, now you have to test a point to make sure it makes sense here. What do we want here? We want the guitars to be greater than 2 times the basses. So greater than for guitars would probably be up here. We want this. Think about it this way. Do the point 10, 0. When you do the point 10, 0 in the equation G is greater than or equal to 2b, if I put 10 in for B, is that greater or is that less than 0? Is 0 greater than 10? Or 20, I should say? No, which means we want to shade this way. So that's what we're going to do. We want to shade false. We don't want anything below this line. So now everything is out over here. So now we're looking at a really small region here. But we have a few more things we need to talk about. We have 2 more inequalities. So let's look back at our last 2 equations. Alright, so my last 2 equations, I'll do this one in green. The base, so x has to be greater than or equal to 5. That would be like, that's a vertical line. And we have g has to be greater than or equal to 17. So I'm going to go to my graph, and I'm going to graph those last 2 and shade them in. Okay, so greater than or equal to 5 is right here. So again, it's 5 is between 4 and 6. Hopefully you guys all know that. And there's my vertical line. And we want greater than. I want to the right of this. So that means I'm going to shade to the left of this line. Alright, so we have that. And finally, we have the last line, which was G has to be greater than or equal to 17. So 12, 14, 16, 17. So here's my line for G being greater than or equal to 17. So if I want greater, I don't want less than. I want to shade false or away from that. And here is my region. This is my region, and this is again why we shade false. It's very clear to see where my region is now. Here are my points where the max or min might happen. We have this one here, this one here, this one here, and this one here. Now, it's very good to get those coordinates, okay? Let's get those coordinates. This one's very clearly x was 5 and y was 17. So I'm going to just put this on here. I have 5, 17 for this one. This one here, well, you have to think about how do I get that equation? Well, you should know what y is here. Y is equal to 17 because it's on the orange line. Well, let's look back at the blue equation, which is actually down here. I put it down here. If my g is 17, I can solve for what b is. So if I have 17 is equal to 2b, I get b is equal to 17 halves, or 8.5. So this point here is 8.5, 17. This one up here, you can do the same thing. The red equation was b plus g equals 50. And we know that b is 5. That's the green line. So I'm going to do that over here. B plus g equals 50. And we know, like I said, that b is equal to 5. So that means g has to be 45. So if those intersection points, you should get the point b is 5, g is 45. And finally, this is the hardest one. You're probably thinking, how do I get those points? Okay, this is kind of why I made these in slope-intercept form, is use your graphing calculator to find the intersection. Okay, so bring your graphing calculator up and type in y equals 2x and type in y equals negative x plus 50. Those are our two equations. I'll show you those in a second. Again, we're looking at the intersection of the red line and the blue line. So we want these two equations in our calculator. The other thing you can do actually is set them equal and solve for b that way. So if you want to do it by hand, you can just say 2b is equal to negative b plus 50, 3b equals 50, and b equals 50 thirds. Which, what is that? That's 16 and 2/3. And that should be the answer for b. When you plug that in, multiply, you can plug it into either one. Negative 16 2/3 plus 50, you should get a g of 33 1/3. And I know I told you guys that I don't like mixed numbers like this, but for this problem, because we're dealing with items, this is the one time that it's actually not that bad. So the last point is 16 2/3 and 33 1/3. Again, I just set these two equations equal to each other. 2b equals negative b plus 50, because that's where they intersect. You can also use your graphing calculator to do that, and I'll show you in class how to do that. So we're going kind of long here. So my points were, I'm going to put these points on here right now. I had 5, 17, 5, 45. I had 8.5, 17, and I had 16 2/3, 33 1/3. Now, let's not do D right now, because this will be something that you don't have to worry about right now. We could talk about that later. What are the number of bases and number of guitars would give the maximum feasible cost? Okay. Well, first of all, you have to use correct points. We can use 5, 17, 5, 45. Those are fine. We can't really use 8.5 and 17, because 8.5, you can't buy 8.5 bases. So let's look at our graph and get the correct point we can use that still fits into our constraints. If you look at here, 8.5 is right here. So we either have to go to 9 or to 8 for the number of guitars. I'm sorry, for the number of bases, because we can't have 8.5 bases. So, obviously, if we go to 9, it doesn't fit in our region anymore, so we can't do that. So we have to use the point 817. 817. Okay? Same thing for this one up here, where we have 16 2/3 and 33 1/3. Now, there is something you can do along this. We can go less and up, or we can go down and less. We probably want to go this way, because it'll probably be better to go up. So I'm going to go down to 16, because I'm never going to go to 17. Notice how that I don't go to 17 here. So this is going to turn into 16, and if this is 16 and it's on this line, they have to add up to 50. That means that the number of guitars would then be 34. So the coordinates I'm going to try to use here are 16, 34, because I cannot use 16 2/3 and 33 1/3, because we can't buy 0.33 of a guitar and a bass. So you have to look at your graph and go, well, which way can I go with these numbers? It has to add up to 50, because that's one of our constraints, and we can't go to 17 for X or for B, because then we're outside of this constraint. So we have to go 16 for B, which makes G 34. So that's the point I'm going to use on the next page, and let's find our max. Okay, again, you can test all these. Our cost function again was 900B plus 750G. And you want to test each point. Again, we have the points 517, 545. We're going to use 817, and we're going to use the point 16 and 34. Well, okay, if you're going to maximize this cost, you could pretty much guarantee that it's going to be one of the bigger ones, one of the ones that were up higher, just because we're putting big numbers in for our values. So but you can test all the points. But you can do that on your own, because you know how to test the points. What should happen, though, is you should find that the maximum point is actually at the 16 and the 34 for G. And you get a cost of $39,900. when you do that. So the maximum cost would be $39,900, and the number of bases would be 16, and the number of guitars would be 34. These two would give us the maximum cost and fit into our constraints. Okay? Alright, sorry the video was long. We did a lot today. Tomorrow we're going to do the second day of notes actually in class. I will also make a video so you guys can go back and review it, but we're going to do that one together because I know you guys are going to have a lot of questions on this. Once you get it though, it's actually not that difficult. It's just a lot of little things. Alright, see you in class tomorrow.